situation that we talked about earlier when we're launching a ball straight up in the air at 40 meters per second. As we mentioned earlier, at maximum height, our velocity in the y direction is 0 meters per second. As well as, if you noticed, the velocity going up is equal and opposite to the velocity coming down at that same point. And lastly, the time that it takes to get up equals the time it takes to get down. So it took 4 seconds to get to the maximum velocity, and it took 4 seconds to get back to the original starting point, which means our total time equals 8 seconds. So the first thing that we're going to do is we're going to use free body diagrams to analyze what's happening with the ball at each second in time. So a ball is thrown straight up in the air at 40 meters per second using arrows as vectors. Draw a free body diagram of the velocity and gravity at each second of the ball travels. So a free body diagram is one where the object is represented usually by a dot, and the arrow represents the magnitude and direction of a variable. So notice we really only use free body diagram for vector forces. Or, excuse me, not vector forces, for vectors, because vectors have a magnitude and a scale. So in this case, we're asked, okay, at 0 seconds, essentially we're asked what is affecting the ball. And at 0 seconds, we launch the ball at a velocity of 40 meters per second, straight up in the air. We also know that the acceleration due to gravity, or our A of y, is pulling the ball back down as soon as it launches. So let's draw that arrow. We have A of y, and for consistency's sake, even though we have an arrow pointing down telling us that if down is negative, in this case, down is negative because I define up and over to the right as positive. Since down is negative, we're just going to say, to keep consistent, negative 9.8 meters per second squared is our acceleration due to gravity in this case. And it's negative because we're pointing down. Even though I have a vector that's pointing down, just to keep it simple to understand, we're going to put a negative there. However, we have a 40 meters per second velocity upwards. So that's a pretty long arrow, and we label this our V initial of y equals 40 meters per second. So then most of you might ask, okay, now we need to get to the next part. We need to do 1 second. Well, after 1 second, what does our free body diagram look like? Remember in class I said the acceleration is tied to our velocity, in that if it's going in the same direction as our velocity increases. If acceleration is in the opposite direction of our velocity decreases. In this case, we could tell that they're in opposite directions. So our velocity is going to decrease. The acceleration will tell us the rate at which our velocity decreases. And this says, for every second that we travel, we're going to go approximately 10 meters per second slower. So that at 1 second, our velocity in the y, notice, is not as high as our original velocity vector, but our velocity in the y equals 30 meters per second, and we still have an acceleration in the y of negative 9.8 meters per second squared. However, there's more than one way to determine that. We use our processing skills on our brains to figure out that after 1 second, we'll be going 10 meters per second slower. However, we can use the constant acceleration equations to prove that as well. In this case, we have the equation v final, and notice I put y because it's in the y direction, equals v initial in the y direction, plus our acceleration in the y direction, times our time. In this case, time isn't really one value, it's really the change in time. So in this case, my v final is what we're looking for. So we're looking for v final of y, and we have our v initial. Our v initial is 40 meters per second. we know our acceleration is negative 9.8, and whenever you have a negative time to positive, you get a negative. So negative 9.8 meters per second squared. And our change in time is from 1 second, our time final, minus our time initial of 0 seconds. So our change in time is 1 second. So now it's just simple plug and play math. I subtract 40 meters per second to get it outside. I am doing it totally wrong. Scratch that. I don't need to do that. V final equals 40 meters per second minus 9.8 meters per second squared. Mathematically, I have meters per second squared multiplied by second. So this and that cancels, and I'm left with meters per second. So I have 40 meters per second minus 9.8 meters per second, which I get approximately 30 meters per second. I technically get 30.2 meters per second, but we're going to round. So I get 30 meters per second, which is the velocity at 1 second. So for the sake of your time as well as mine, I'm just going to fast forward to what happens at 4 seconds. So at 4 seconds, we still have an acceleration due to gravity pulling down at negative 9.8 meters per second squared. However, after 4 seconds, since we started with 40 meters per second, since our V final y equals our V initial y plus our acceleration y times time, our time here is 4 seconds. So if I just plug that in, I get 40 meters per second minus 9.8 meters per second squared times 4, which I get approximately 0 meters per second. It's actually like 0.4 seconds, but in this case we're just going to round for simplicity's sake. So at the very top, my velocity in the y direction equals 0 meters per second. So therefore I have no down arrow in the v of y because v of y is non-existent. And just to fast forward in time, so if I go to 5 seconds, my free body diagram is still going to have acceleration in the y the same because it never changes. The only way we could really get the acceleration due to gravity to change is if we blew off a chunk of the Earth and it went out into outer space and we changed the mass of the Earth. After 5 seconds, I've accelerated down 10 meters per second squared, which means that my velocity at 5 seconds in the y is also negative 10 meters per second. So let's jump to the 8 seconds. At 8 seconds, we want to know what is our final velocity and our gravity. So our gravity, once again, a of y equals negative 9.8 meters per second squared. And our velocity in the y equals negative 40 meters per second. So we can never really assume that when we launch a projectile that the final velocity at the end is 0. It's 0 after it hits the ground, but we're considering it the instantaneous point it hits the ground, or in this case comes back to the same point.